evening, everyone. Okay, stop talking, please. Okay, can you stop talking, please? If you need to form a group or to discuss your quiz result, you can do it in the lab. Okay, we need to start the lecture now. Okay, so this week we'll continue with Neo4j, and as usual, like last week, we covered the basic data model and how you can run queries. And this week, we're going to see a little bit like on the server side, how data is stored and how query is carried out. So for, the previous week is more like from the client perspective, how you like write a query, how you store it, like how you describe your data and how you write query. And here is more from the server side, how your data is actually stored and how like what query is executed by the server. And we also cover a little bit on very, very simple and basic few data modeling principles, very high-level principles you can use on Neo4j. Yeah, so that's the outline. So it goes through like storage, like query plan and indexing, and then we see data modeling and a little bit graph algorithms. Okay, so yeah, Neo4j had used this property graph model, and there are a few core concepts in the property graph model. The data is like this, like a graph, and there are nodes. And nodes can have labels, can have multiple labels, can have no labels. All these are labels. And then nodes can have properties. And then we have relationship between nodes, and the relationship can have directions and can have no directions. And relationship can have types, and also relationship can have properties. So these are the core concepts in the property graph model. Okay, there are a few things that needs to be highlighted. First, there's no table concept at all in Neo4j. So it doesn't really matter how many things you stored in Neo4j. It's like a big graph, and the big graph can have very independent subgraph. They don't connect to each other. They're about very different things. So, but anyway, the whole database is a large graph, and even though they're independent subgraphs and they don't connect to each other, and still there's no way you can say this is a table. So on the same server, if you really want to separate things, if you think this like there are things belong to a totally different domain, you don't really want to put them in the same like database, because you probably have like on the two domain you may have node with same like labels, and you don't want to get mixed up, and they refer to very different things probably in the two domains. So it's possible to run multiple Neo4j instances. So each instance represents like a database. So you can run multiple instances on the same server, and then to have some separation of like conceptual separation of your data models. But if you really want very strict isolation, and then you need to configure them really properly so they don't really share anything. Like all these instances, they don't share anything, even though they share the physical server, but they don't share anything else. Like they're quite independent. And so the logical data model, which is a property graph model, we've already seen that in any storage system, the logical model, like the model, the client views can be totally different to how the data is actually stored. Physical, like the physical model, physically stored on a hard disk. So Neo4j is similar. Theoretically, we can actually we can construct this property graph model with any storage backend. We just load the data and then construct like a model in the memory. But that's not the ideal thing if we have a lot of like queries and things like that. We really want to design a storage system, to design storage here, like together with the logical model, so that we can get optimized query performance. That's why theoretically it's possible, but for performance, for better performance, actually Neo4j does design its own storage backend. It looks very, very different to any other storage system you have seen. So there are a few features, and which we will basically explain later what it means. So first, it provides like native storage of relationship between nodes. So it's like the storage itself basically reflects the relationship. So it's very effectively like a pre-computed bidirectional join. It's like pre-joined. You don't really need, if you want to find the relationship, like a very long relationship or very long paths, and you can, this is basically reflected in the storage. You don't need to run like complex query, complex join on top of it. And the traversal is a graph. For any graph, the typical way is to traverse the graph, like from one node to another node, following the relationship links. It's very, again, it's pretty native. It's like pointer dereferencing, just following the pointers and figure out what's at the end of the pointer, and then we're going there. And it has index-free adjacency, so the adjacency doesn't really need another like neighborhood of the node, doesn't really need additional index structure to support it. Again, it's reflected in the storage. And so it's basically, that's like, it says it's much cheaper than the global indexes. The way they design the storage to reflect those relationship and the structure, making it much cheaper than having a global indexes to represent it. Well, the overall architecture, it does have a lot of similar components to other, like most storage systems will have something to manage the disk, like or different files, and manage the memories and disk to memory things. So there are like cache and managing concurrency, like log, or managing transactions. So these are quite similar. And on top of that, we have like different APIs. Okay, so we are more interested here in this lecture, like what the record file looks like. How does it make it like reflect the native like structure of the graphs? So it's mostly like what the files looks like. Okay, so there are so each database consists of a few files. So any storage system usually consists a lot of files. So here again, Neo4j also store its data in like regular files on your regular operating systems file systems. So most of the other systems, the files are more like correspond to like the tables or the collections. But Neo4j doesn't really have that concept. So the file actually corresponds to the core concept, like nodes, relationship, properties, and labels and types. They all have corresponding files. And so property is stored separately, labels stored separately, and types stored separately. So basically, the overall design principle they try to follow is to separate the graph structure with the actual data, like the properties. So because they want to have like fast traversal, so they want to store the structure as well. And another thing that is unique is, so most of the core concept, like node, relationship, even property, and label, actually, and type, they all have system-assigned IDs. So those IDs are assigned by system. You can't really change it because the ID is it's an important system feature. It's related with where the data is stored. So you can't really change it. Even if you give you declare a property called ID and then give it some value, it's not the system-assigned IDs. And all of this, and another feature is everything is stored as a fixed length record in respective stores. So node, relationship, and property label, they all stored in like fixed length records. So each one is stored in a record, and the record is of fixed length. So this is basically the user's view of their graph and the actual record on the disk. They are structurally dissimilar, but the storage is trying to facilitate the graph traversal. So still reflect the structure and everything, but it looks quite similar, quite dissimilar. Okay, now let's see a few important files, what it looks like, and how does it make it very efficient in traversal. Like we can do very in-depth traversals, like following a very long path in Neo4j easily. Okay, so let's first see the node store. So how node is stored. All node data is stored in a single file called the node store file. And depending on the versions, the store files have slightly different names. Currently, it's stored in a file named neostore.nodestore. And that's the file. And it's not like a text file or Word file or any like Excel file. So it's a file written by Neo4j of following its own structure. So the file consists of fixed-sized record. And each record corresponds to a node. And each record is 15-byte long. That's fixed-sized. It was 9-byte in the early version. And so each node, remember, has an ID, right? And its record is basically stored on the offset computed by the ID. So that's the offset of the node record is basically the node ID times 15. 15 is the byte. So if the ID is 0, it's stored in the first record, and offset is 0. If the ID is 1, it's stored in the second record, and then the ID is 15. And if ID is 100, and then it's stored in the offset 1500. It also has a few so that's the main file for Node. It also has a few like accessory files to store other like important metadata. Like there's a file which stores deleted ID, like IDs. Like if you create a node, and then after some time you delete it, and then which means this ID is not in use and can be reused later on. So it has a file to basically store all these like deleted IDs. And then the system will scan it to see if do we need to add an extra record for a new node, or we have some unused nodes. We have some deleted IDs that we can use, so we don't really need to create an extra record. So this, so it only has 15 bytes, so you can, and it doesn't really matter how many properties a node have. One node may have one property, another may have 100 properties. They're all stored in the same fixed size record. This is because we don't really store the actual property in this file. It's stored somewhere else. So this one, it's mostly store like pointers, pointing to all different things. So it stores quite a few pointers. The first byte is like, it's an indicator whether or not this record is in use. So we do have a place to store like deleted IDs, but we might have some extra record that we created but not really in use. So anyway, so it's always convenient to have this flag inside the record itself saying whether it's in use or not. And then the next 4 byte is a pointer, actually remembering the ID of the node's first relationship. A node might have no relationship, might have many relationship. If it doesn't have relationship, that's okay. We don't need to store anything here. There must be a special marker. And if it has many relationship, we store only one of them. One of them's ID, actually not storing the whole relationship, but storing the relationship's ID. And using this ID, so it's like a pointer. We can find the actual record of that relationship. And the next 4 byte is for the property. It's the property ID. So it's another pointer. It stores the ID of the node's first property. And well, it doesn't really, the order is not that important. So a node might have many properties, and depending on when the node, the order of the creation, like when you assign the value to the properties. So one of them will be like the first one, and it has an ID, and the ID is stored here, and all the others can be found from this one. So we only store. So this is the pointer point to the property, and then we have another pointer for the labels pointing. It's like the ID for the labels. Again, not storing the actual label, but the ID for the labels. And again, it doesn't really matter how many labels you have. We only store the ID for one label, and all the others can be found from the first one. So it has a lot of linking thing here. And then there's the last one is like an extra one for later use. At the moment, it's not really used. So that's for node. We remember it's like first relationships ID, first properties ID, and then it's first labels ID. So it contains 3 pointers, basically, for its 3 important things. Now let's see how relationship is stored. So again, there's a particular file storing all the relationship data. It could become pretty big. It's stored in a single file, and depending on the versions, the file name could be different. At the moment, it's called new store.relationship store. And the structure is kind of similar to the node one. It also consists of fixed size record. Each record represents a relationship, and each relationship has an ID, and the relationship is stored on the record where its ID, where the offset is computed by the ID. So each record is, the fixed size is 34 bytes. We store more things about the relationship than node, so it's a bit longer. It's 34 bytes. So the offset of the relationship, again, is computed by relationship ID times 34. So the first relationship, if the relationship ID is 0, it's stored in the first record. If it's, and offset is like 0 byte. And if its relationship ID is 1 and stored in the second record, and then the byte offset is 34, and so on and so forth. So similar to the node record, the relationship record also stores a lot of pointers. It doesn't really store its actual properties or types, but it does store a lot of pointers. Each pointer points to different things. It has so many pointers, actually. Let's see in what each pointer is. What are these pointers? And later on, we will see some examples. Okay, as usual, relationships can be deleted, right? And then its ID will be collected in an accessory file for all the deleted IDs, and then that can be reused. And we also reserve a byte as a flag to indicate if this record is currently in use or being deleted. So there's 1 byte for as a flag, whether or not this is like a valid or active record. And then any relationship has a source node and a target node, right? So that's something important about relationship. So we have a pointer to that. So this is the first node's ID and then second node's ID. So this 4 byte is about its source node's ID, and this 4 byte is about its target node's ID. And then relationship can have type, and the type again stored somewhere, and it has an ID, and then we use a pointer to that. So the type has an ID, and we store the type ID here. And then there are after this there are 4 groups of pointers. Each pointer stores a relationship's ID, some relationship's ID, but not a random ID. It has some meaning. Okay, so this stores the ID of the first nodes, like previous relationship. So the first node, like the source node, in addition to this particular relationship, has lots of other relationships, right? And then we try to connect all this together. So this stores the first node's previous relationship ID. And this stores the first node's next relationship ID. So by doing this, basically one node's all relationship can be found. Once you locate a particular relationship of a node, you can find all other relationships this node has by following these links. And we do the same thing for the second node. Second node also may have other relationships in addition to this one, the current one. So we use a pointer to point the previous one and the next one. So basically, we put like all the relationship of a node in a long list. And a relationship can have property as well, right? And again, it can have many properties. So we don't store any of the actual properties here. We only store like a pointer to one of its properties. We call it the first properties. And then from that property, we can find all other properties. So everything is kind of linked. So there's a pointer as well for the property. Okay, so like for a relationship, we store its source target and lots of other relationships, and forming many links actually, and also its properties and its type. So that's why it's a bit larger, because we store a bit more things here. And this another special marker called the first in-chain marker. So this is whether or not this is the first in one of those like the relationship chains. Okay, so these two are the most important files. There are other files, and it's a bit the Neo4j documentation doesn't really give very detailed like layout of how those files are organized. The only thing we know is that most of these are actually organized as fixed size record as well. So there's a property stores. It contains fixed size record to store properties for the nodes and the relationships. So it's one of them. And storing, it doesn't really separate node or relationships properties. It stores all the properties. And the simple properties are stored online, like simple things like integer, like float, because they are already like, they fixed lengths, right? So we can store them. So int, you can have 32 byte or 64 byte. They're fixed. Or if it's character or if it's byte, then that's all fixed. They can be stored inline with the record. And there are complex properties, right? We might have a property of string type, which is very variable length. Could be a short string. It could be a very long string, so it's not fixed. Or we might have an array property. Again, it contains contains like items, and it can contain a very number of items. So that's not fixed. So all of this they are stored elsewhere again with a pointer to it. And the label, node label, is also stored in like something called label store, and then also actually type is stored in a type store. Like the relationship type is also stored separately. So most of them have like fixed size and then have something, have an ID. All of this have ID because otherwise you can't really refer to them. And they have ID and they have link pointing to the next ones. Okay, so we've seen from here, like for all this node, whether it's node or relationship, we always use like 4 byte to store its ID. So that means, yeah, there's a maximum, right? Well, the theoretical maximum, but the system might reserve certain values as special markers. So the theoretical, because it's 4 byte, both node ID and relationship ID, they are 4 byte, means 32 bits. So theoretically, the maximum ID value could be 2 to the power of 32 and minus 1, if every possible value is used as the ID values. But if the system reserves special values, and then the maximum probably is a bit smaller, a little bit. You can't really. Maybe the maximum value, the ID is used to indicate something special. But you can have as many as that. So this also restricts the size of the database, right? Because if the theoretical maximum ID value is this, so that means you can have the maximal nodes you can have is this, and the maximal relationship you can have, number of relationship you can have is also this. So it can't really, the graph doesn't really grow to like infinite size. And the IDs is assigned and managed by the system. So the system will remember which ID is assigned, which is like deleted and can be reused. And the corresponding record, remember, they're always stored in the computed offset. So that makes it really easy for us to find any record once we know the ID. And we just need to, once we know the ID, we know the offset, and then we know this block which has it. Okay, now let's see like example how like what should be the value of these things. Let's see, like first let's see node structure. It's relatively simple. It doesn't have a lot of pointers. So assuming we have a property graph like this, we have node 1 and node 2, and node 1 has 2 properties. One is name, the other is age, and it's of the label person. And node 2 is also have the same label called person, and it only has 1 property called name. And then they currently have a relationship called likes. And this is the source, and this is the target of relationship. And node 1, apart from this, has a few other relationships, and node 2 again have a few other relationships. Okay. So let's see what's the record corresponding to node 1 would look like. It would be like this, right? The first, it contains 3 pointers, right? And 1 in-use byte and 1 extra byte. Okay, so that's the whole thing represent the node 1. It's in use. And so the first, after the in use, the 4 byte is the next relationship ID. It might not be this one, so it's one of its relationships ID. So it could be this one. The first relationship of this node in the relationship store, the ID of the first relationship of this particular node. And then we have 4 bytes to store the property ID. So which, assuming the first property is name, so that's basically stored ID of this one. And this one, we don't really, so from here, there's no direct link to this one. So if you want to find all the properties, basically you have to follow the property links. So you find the first one and then go to the second one. And then, yeah, so this is the pointer to the first property. And then we have a pointer to the label, which is this one. It's a 5-byte pointer to the label. First label of this node in the label store. And that's first, and here is the only one. So the actual property, like age, is basically linked here. So in the record representing this property, there will be a link pointing to the next property, basically. Okay, so if we want to get all the properties of a node, but we start from the node, we find the first one, and then we follow all the links. We traverse the property file by following the links. So each property, if it's not the last one, will have a pointer, which the pointer's value is basically the ID of the next property. And then we follow that, find the next one. The next one, if it's not the last one, we'll have another pointer. So like we basically traverse the property file by following the links. So that's the node structure. It's relatively simple. Now let's see what the relationship structure would look like. So the relationship is like this: Bob likes Alice. Okay, let's see what this. So again, that's like a 34-byte record. So the first again is in use. Means there's some value indicating it's active record, others indicating it's not active one. And then the first 4 bytes remembering the source node. So it will store the ID of node 1. And second will store the ID of the node 2, right? Its source and target. And then we will have 1 to store its relationship type, which is relatively easy. And then next we have a group of 4 relationship IDs. This is storing. The first one stores the node 1 Bob's previous relationship, which is this one. So suppose there's a previous relationship. So there could be, so all Bob's relationship is kind of connected here like a link. And this is the previous one. And then each one will point into its previous one. So we can go from here. And then it also point to its next one. So it's like a double link. Point to its next one. So each one point to its previous one and next one. So we can traverse it in any directions. So it's the next one if it has quite a few relationships, and this is somewhere in the middle. And then this point to the next one. So the previous and next, it doesn't really have any business value here so the user, the client, doesn't need to know it at all. But the system basically just uses a simple way to decide. One simple way to decide is based on the relationship creation time. The first one being created, it's like the first one, it will be stored in the node, and the second one is like the second one, and so on and so on. So that's, then we have we have an order for the system to facilitate traversal, and the order the user doesn't really need to know actually. It's all managed by the system, pretty transparent to the users. And that doesn't have any business meaning at all. So similarly, we do the same thing for the second node, which is node 2, and its previous, and if it has many relationships, and then we have a pointer to its previous and next. And if it doesn't, then again, we have a special value to indicate none. So that's the previous, and that's the next. So this is what we call doubly linked list. Yes, so basically from a particular relationship like this one, possible to find all relationships belonging to the source and target node. And finding them is quite simple. You don't need to do any drawing or anything. It's all like following the pointers. And the pointer will give you the offset. Just by a simple multiplication, you find offset, and then you locate the record. Okay, again, let's see a running example. How the whole thing is working like how the system decides to put what value where. So assume we have a very simple, we just start creating the graph, and then this is with like 2 nodes and 3 nodes and 2 relationships. It's like a friendship graph. There's a node representing people, person, and then relationship like who is following who, or follows, like a Twitter follows relationship. Suppose the creation order is like this. First we create Alice, that's the first node, and then we create Bob, we create Charlie, and assuming they were assigned subsequent numbers. Alice got ID 1 and Bob got ID. Alice got ID 0, Bob got ID 1, and Charlie got ID 2. And then we create relationship from Alice to Bob, like this one, and the system assigns ID 10, and then we create another relationship, Alice to Charlie, this one, and the system assigns an ID 20 to this relationship. So that's one, that's this. Now let's see what happens after we execute this creation command. So that means in the node file, we will have 3, after this actually is three command, create node. We have 3 record, and they all, here I use 1 to indicate it's in use, but could be different values. Neo4j document doesn't really say which values. I'm using 1 for simplicity. So this record is the record for the Alice node, and this is record for Bob node, and this is record for Charlie node. So they are next to each other because their IDs are next to each other. So this is offset 0, and that should be offset 15, and that should be 30. So then currently they have, when we create this, we give them a property like the name. So we have a property here. So we need to put the name, the actual property, in the property file, and then we get the ID, and then we add the ID here, pointing to this name, Alice. And this is of person type, of person label, so we need to create the label and put it in the label file, and then we get an ID, and then we put the ID here. And similarly, for all these 3, we do the same thing. So at the moment, none of them have any relationship. So this record is currently doesn't have, so not this record. So this portion of the record doesn't have any value. And then we create the 2 relationship. So they are stored in the relationship file. So that's the one representing this relationship with ID 10. So it's on offset 340 because it's 10. So 10 times 34. And again, the first is like in use, 1. And then this one, it's from Alice to Bob. So we have source, we have a target. So the source is here and the target is here, right? And it has a type called follows. So we put a type there. And at the moment, we don't really have other things. It might have properties. If it has property, we put it some. So we need to create a record in the property file, and then we get the ID and then put it here. At the moment, there's nothing here because this is the very first relationship in the whole system. So Alice doesn't have a previous or next, and Bob doesn't have either. So they are empty. Now, but after we create this relationship, and because this is the first one for Alice, so we need to update the node record as well. So we put this. For Alice, the first relationship is of the ID is 10, so we put 10 here. And there's also the first one for Bob, so we put 10 here. So now both Alice and Bob's records are complete. It has all the important pointers with values in it. Now we create another relationship. Now this one, the system assigns like an ID 20. It's not next to each other, so it's after some byte. So so the offset is 680. So basically 20 times 34. And again, it's an active record. So this is from Alice to Charlie. So we need to put Alice here. We put Charlie here. Charlie's ID is 2, right? So there's 0 and 2. And the type is follows as well. It may have some properties as well. And now, this is the second relationship in the whole system. And once we have a few relationships, we can start to build a relationship, doubly linked list now. So now, first, so remember this 2 is about Alice, right? Alice relationship. So this is the second relationship of Alice, right? Alice's first relationship is this one. So it does have a previous one, which is this one, and this ID is 10, so we put 10 here. And then, which means for this one, now Alice has a second relationship, which means here the next should be 20. So we put in here the Alice next relationship is 20. Now we connect these two relationships together. So it has a pointing forward and pointing backward link. They are linked to each other. And also this, because this is the first relationship of Charlie, and we need to add a link here. So Charlie is able to find all its relationship starting from a single one. So we put 20 here. Now Charlie's node record is also complete. It has its first relationship, has its property, and it has a pointer to the labels. So that's for this simple one, that's what the record looks like. We do have quite a few record with values that's not really filled in because there's nothing, we don't have any values to fill in. Now, to make it a bit more complicated, to make the linked list a bit more complicated, let's just add some extra one. So this is currently when we have 3 nodes and 2 relationships. That's our node record. We have 3 node record and 2 relationship record. Now, assuming we just create another node and also a relationship. The node is called Daniel, and we give it ID it's 3. So the node will occupy the record right next to this record in the node file. And at the moment, we have, its name, its property. We have a pointer to the labels. And next, we create a relationship from Charlie to Daniel, like this. Charlie follows Daniel. So we give it ID called 21. So 21, that means it's a record right next to this one. So with offset 714, basically plus 34. So this is a record right next to this one, representing this relationship. Now this relationship, it's from Charlie to Daniel, it's 2 to 3. So we have 2 and 3 here, that's source to target. And we have some type, we have some property, which I'm not, so that's as usual. And now, this is the second relationship of Charlie, right? And Charlie, this is Charlie, like source, and this is about the previous and next of Charlie. So Charlie already has a relationship here, which is this one, which ID is 20. So we can fill in the portion here, like 20. So this is like Charlie's previous record, a relationship. Has an ID 20, so we put 20 here, which is basically this one, and then we need to update this as well because that's like Charlie's next record is 21. it should be actually, what did I do that? Sorry, that's 10. That's the, let me see, did I make it wrong? No, this is, so that's Charlie's, so it should be here. That's, 20 is here and 21 is here. That's the for Charlie, and we put a 21 here. That's already there. Because Charlie is this one. So this 2 is Charlie. So Charlie's next is 21. And this is Charlie's first one, so it doesn't really have the previous one. Okay, and then we put 21 here. So we also update the node record of Daniel here. Its first relationship has ID 21. And so that's the, so for here, it doesn't really have next one, and then for Daniel, it doesn't have previous and doesn't have next because this is only one. So that's so far all the things we have. So all the node records, basically they complete. So every bit of information is filled in. But for relationship, there is still a few component. It's kind of doesn't really have value because we don't have many relationships. Now let's see how we can use this doubly linked list to actually to match the patterns, traverse it and then match the patterns. Now suppose we are trying to answer a query like this, match like a person called Alice to some other person, and then the path is 2. So basically we want to find all the paths start from Alice and then to someone else, all the like length 2 paths. So this basically is a length 2 path, and this is not. By looking at the graph, you can manually figure out it's this one. But the system needs to work out by looking at all this record. And then we return the others. So how do we do that? First, we need to find Alice. So the system has a way to find it. So assuming it's pretty easy. So we find Alice record relatively easy by using index or whatever. From the property, we are able to find the actual record, which has the property. Node record has property. So it's here. Right. So the first thing is find a node record. And once we find this, because we're trying to find some paths, all these paths are formed by relationship. So we need to follow the relationship, and then we find the first relationship, which is this one, and it says ID is 10, and then we jump to the relationship file, and then we find the record at offset 340. That's the record we want. That's the record representing relationship with ID 10. And once we find that, so it's basically this, because we want a path to the length to pass. So which means we want to go from Bob. So it's like from Bob, from this target, we want to go either up or down. So we check here to see if we can go anywhere. So we find this, and then we check if we can follow any paths of Bob's. But both are kind of like empty or null, so which means Bob doesn't really have any other relationship except this one. So that means, yeah, we have to stop here. It's not really a candidate. So stop here on this branch, and this doesn't really give us any potential result. So it's like we're doing a depth first one. And then, so what we need to do is now we try to see if Alice has any other, because we only explored one relationship of Alice. And this relationship doesn't really give us anything. So we want to see if Alice has any other relationship. So how do we find out that? We have to check this too. we can go either this way or this way, because this is where we can find all Alice relationship. That's the link for Alice relationship. So luckily we have a value here. Says okay, the next relationship is like 20, and that's basically Alice next relationship. So it's like we go back to Alice and then try another branch, and then so we come here. It's 20, so we go to this record, offset 680. And again, we do the similar thing. Once we arrive at this one, we want to see if the target node has some relationship that we can follow. That means length 2 pass. So we find this, and now we check these two positions, these two portions. And then there's nothing there, but we do find something here, which means, okay, Charlie does have a, we don't need to go to the actual Charlie's one because we're not interested in the node. We're only interested in if it has a relationship. So we go here and find, okay, it's 21. So we go here and we find 21. So that's another relationship. And that means, so this is actually like a candidate, like one result, because it's a length 2, right? We go from Alice to Charlie and then to another one. So that's a result. So because we are interested in the node, so we now look at, okay, what is the target node, and we find Daniel. So we look at this, and then we check this node record, and then we find it's Daniel. And then, so that's one result, but there could be others. So how do we find the others? Is we try to see, now we arrive here, we try to see, like, basically we are here, and we don't need to go from Daniel, right? That would mean length 3. So we basically go back to Charlie to see if there's, and Charlie has further relationships. So we go back to Charlie's one, and then basically we need to check this and see if it has a further one. Because we're following the forward one, so we don't go backward. We check if there's a forward one, there's nothing. So means nothing, we can't go anywhere from here. But that doesn't really mean the end of the search. So Charlie has no other relationships, so we don't need to worry about Charlie. So we stop here on this branch. But that doesn't mean we stop searching for the result, because Alice probably may have other. If Alice has followed someone else, we should check that as well. So we need to go back to Alice and see if Alice has other relationship. And basically go back to Alice, we check here. Now we're in here, and then we check, okay, if Alice has any other relationship, because that's Alice previously, and that's Alice, so this is Alice, right? So that's Alice previous, and that's Alice next. So Alice doesn't have anything. So we're already at the last one of Alice. And then we stop here. So which means that's basically this is the only one. So Alice is the starting point, and we don't need to explore any further, and we can stop here. So that's all this pattern matching, basically. Eventually, when it's executed by the server, it becomes like following the point. And all the point will tell you, and all the point will point to a record. And the record is always in a location where it's very easy to compute where it is. So yeah, they're concerned, so the node and relationship stores, they're only concerned with the structure of the graph. It had so many pointers. And it basically contains lots of IDs, and each ID is point to some record. And not the property data at all. And the both stores use like fixed size records, so any individual record's location can be easily figured out by once you know the IDs. And so these are the very critical design decisions that underlie this Neo4j's. They have a commitment to high performance traversals. Okay, yeah, I will stop here and give you a 10 minutes break, and then we will see the actual query plan, how server decides what the steps that the server use to answer complex queries. Can everyone go back to your seat? We'll continue with the rest of the lecture. So just now we show you how the server can do this pattern matching by following the pointers in node and record, node and relationship records. Now let's see. So that's like a very low level detail, low level thing. But now let's see like higher level when the server receives a query, how does it start, and then how to build at different stages of the query. Okay, so similar to any other storage systems, there is a component in Neo4j that will basically read the query and then convert it into an execution plan. So that's called execution planner, and then usually the execution planner will figure out maybe a few plans, and then if there are alternative plans, then we'll use that, and we'll use certain information to choose which one is to pick the optimal one. So it does have a few strategies, and early days they has a rule strategy planner, which will consider indexes, but not really statistical information when it's designed a planner and picked a plan. So statistic information is like the data, how many data we might have for this particular node or particular relationship. And but again, in the later versions, they build more sophisticated planners. So they try to use the cost-based ones, which is most other storage system basically use. So utilize both the index, and if there are multiple indexes, and you will decide which index to use to using statistical information of the data. So the index that will give you the smallest subset to start with, usually you use that one. So Neo4j does that as well. So it uses statistical information, basically evaluate if there are multiple plans, to evaluate the alternative ones, and always use the ones that will give we want to start small, right? And then there's usually cost less. So for instance, if there are multiple nodes and node labels, and we can start from either one, and if we know that there are less movie nodes than the person or people nodes, and a query involves both, usually we'll get better performance if we start from movie side instead of the people node, because this is much less and this is much more. And you will see example in the lab, actually in the tutorial, in the lecture as well. So the query plan has multiple stages, and then depending on how complex it is, but they always have a starting stage. They always have a few stages, even very simple ones will have it. So the first stage is always a starting point. We want to find what is the starting point. And then once we have the starting point, and usually followed by expansion, because most query will have a pattern, right? And then you need to do a pattern matching. And the pattern matching is is usually implemented in the expansion stage, basically starting from the starting point, and then we try to expand by following the relationship and see if we can match the patterns in the query statement. And then after that, we probably do the filtering, or we might do the filtering before, and if we have conditions like the node or the relationship conditions for their properties, and then we can do that. Okay, we do skipping, we do sorting on other things, and then we may have to combine some operations. And later, and then if it's update query, we may need to update things. So these are the typical stage. Most query will need to have. Let's see them one by one. Let's actually see a query plan first, an example. So here is basically we want to find all directors of the movie Cloud Atlas. So we definitely have a very, very clear information is like the movie's title is Cloud Atlas. And then we want to find all the directors for that one and return the director's name. So this is how we write the query. This is like that's the movie node, and then there's a director node, and then this director relationship, and then we return director's name. So assuming there's no index created yet, and also because we're not writing, when we write the query, we're not really paying attention to it. So when we write the query, we didn't really indicate the labels here. So here it's just like a node with a title called Cloud Atlas, even though we know it's a movie. But if you don't really put the movie label there, then the system doesn't really know. The system only knows, okay, you're looking for a node with title Cloud Atlas. And here you're trying to find some other node with direct relationship to it. And because of that, because the only thing we know is the properties, and we don't really have IDs. And so we still have to start from here. But to find this particular node, we actually have to do an all-node scan. So we have to check all the nodes, basically, and see if it has a title called Cloud Atlas, and then to find our real starting point. We'll start from all-node scan, and then do a filtering to find the node which has a title called Cloud Atlas. And once we find a node, and now we can start to do the matching, to match the patterns, to expand. By find the direct relationship and then directors. And after that, after we expand that, we find all the matching passes, and then we can find the target node. And then we do a projection to find its names, like search the properties file to find the name properties. So Neo4j provides two ways for you to check the query plan. If you only want to, if you know the query is quite expensive, you only want to get some, and you probably have a few ways to write it, and you want to estimate each different way's cost, so you can use this explain. So this won't really run the query, but it will give you some estimation, like, okay, how many rows will be involved in this, and how many rows will be involved in that, blah, blah. Or if you only have one way of writing the queries, and you're not really trying to estimate, you actually try to see the real one. You want to run it and then get the real statistics, and then you can put a profile in front of your query. You get a profile. Basically, that's so this is estimated like plan, and this is like the actual one. So you run the query and collect all the statistics, and then tell you, okay, when I'm doing the all-node scan, so it returns that many rows. And then after the filtering, I only get one row, even though the plan says there might be 18 rows that having this title, but actually I only got one row. And then this expand all this says after the pattern matching, we might have 4 estimated rows, like four paths match the patterns. But this is like only have 3 paths match the patterns. And then get 3 directors and return the name. So the DB hit is something a little bit vague. It really depends on the versions and other things, so you don't need to worry too much about it. Sometimes it's same as the number of rows, or slightly different, and sometimes it could be quite different. So it basically kind of like how many disguiles, but how they define it, it's really, there's not very, it does have some, when you check the document, it does list a few things as considered as hits, but it could consider as 1 hit or 2 hits. So this is more explainable, and this is a bit vague. Yeah, there's opt and all nodes, and then the property by checking the property file, then direct the relationship of the Cloud Atlas, and then find all of them. Okay, so let's see. So this particular example, the starting point is all node scan. or as bad as you can get, you usually don't really want to start like that. In particular, if you have if your database is pretty big, has so many nodes, you don't really want to start. But that's an option. That's option. It should be your last option. Like if you don't really have any other way, and then the system might have to do that. So that's so starting point. So most of the queries start from nodes, like either one or a set of nodes or all nodes. Most likely we start from nodes, except only in one particular condition. And that's usually not very likely you're going to write a query like that. So only if you specify a relationship ID. Like if we want to find the node, the source node of a particular relationship where the ID equals 0, and then return it. But usually you don't really get this, and it doesn't really have much business meaning. But if it's a query like this, if we give a relationship ID, and then, because that's a natural starting point, right? By looking at the ID, we can really easily find the actual relationship record, and then we can find these two things. We don't need to follow any pointers now. But unless this is given, in all other queries, it's starting from the node, because there are a lot more. The node has a lot more features to allow you to make a relatively small subset of that starting point. Like the property is like indexed, while the relationship's property is not really indexed. Okay, so query may start by scanning all node, as you already seen in that example, or if we just want to return all node, so that will starting from by scanning all node, basically by looking at the node, load the node file, right, and then just check all the active record one by one, and then return them. Or like this one, because we have no record, and we didn't really specify the actual node labels, so then the system has no way but to basically inspect every single node. It could start by scanning all nodes belonging to a given label, so that will make your starting point much smaller. Like if we say match person, with name is Tom Hanks, and return this. And then, because so the labels are actually implicitly indexed. So we don't need to check all the nodes. There's so many nodes that doesn't really belong to a person. So we only need to check all the person nodes. And there's an index which will tells you what are like all the IDs of the node record belonging to the person labels. Or query may start by using index. It's like the index of the node properties. So if we have, like here, if we index the property name, and then obviously that's a better way instead of scanning all nodes. So we can use the index to find which node actually has this property. Has the property of value of Tom Hanks. So using index obviously will give you the best performance if there is an index. So that's the starting point. But let's see example of query starting from labeled node. Now, if we want to find like the degree, the node degrees of the person node, or the person node, so we like match like a person. So we indicate this is a person node, and then there's some relationship to something, and we don't care what's the other node, and we don't care what's the relationship type. So now, because we only want to find out the degree, like how many links are there, how many relationships are there. So then we do aggregation. So that's the grouping key by the actual node, and then we count something as a degree, and then we order by degree and return 1, limit 1, and then return it. It's like we're returning the node with the least smallest degrees. Okay, so we scan. So this starting point is not scanned by label, right? Not like all. and it has like 133, so which means we have 133 person node. And then we do an expansion. So we try to find all the, for each person node, we try to find all its direct, like not direct, so all the relationships connecting to it. And then we do, so once we find this, so aggregation is done in the memory. So this one doesn't really have DB hit or anything. So it's done in the memory. And it still has, so this one has that many rows because it has this many nodes and that many relationships. So in total we have 256 rows. So some nodes may appear in multiple relationships, right? And then we do the aggregation. It's all in memory, so it doesn't have any IOs involved. And because we have that many unique nodes, so again we return that many rows. So each row represents a unique node's degree count. And then we do the top, and then we do other things. So all of this kind of like a memory processing doesn't really involve any DBs. So only the first two stages involve DBs, like IOs. Okay, let's see some query plan with index. So yeah, Neo4j supports index on properties of labeled node, right? So the index has very similar behavior as those in relational systems, and it's like a B-tree index. It can be built on single or composite properties as well. So you can build index on a combination of properties. And we've already seen that's how you create or job indexes. Now if we want to see, find all the things in the database that has like 1 to 4 degree, 1 to 4 like length pass to Kelvin Bacon, and then return all the distinct ones because there could be duplicated ones. So how do we do this? And you will find the start point is not index seek, not full table scan or label scan, but index seek, and this will just return a single node. So we start from a single node. And then we need to do expansion because here now we are doing like not fixed length expansion because it's like the length could be 1 to 4. It's variable length. So we do a variable length expanding starting from the single node, and then we find all the, so there are actually many matching paths, and we find that many matching paths. And then we do a distinct, and again the distinct is more like once you get, this is how you get the candidate, and then we do some memory processing. We do distinct, and then we return the result. Okay, now let's see a few more query plans, something more like a bit more complicated. Query and its plans. So that's a query. Yeah, this is what we want to find the person who shares like a phone number with Tom Hanks, right? That's the query we've seen in last week's lecture. So we match a person whose name is Tom Hanks, and assuming we have built an index on the name property of the person node. And then we unwind all the phones and as phone, and then so we have a subquery, and then we try to match with some other person's phones. So this starts from, this is like a node seek index, and then we find Tom Hanks, a single row, and then we do a projection here because we're not interested in all the properties. We're only interested in the phone's properties. So we do a projection, and we also bring down n. And then we do an unwind, and after we unwind, now we get 2 rows because assuming Tom Hanks currently has 2 phone numbers. So after we do the unwind, we got 2 rows, so 1 for each phone number. And then we have subquery here, which we try to use this to check, like, if any other person has the same phone number. So which means now there's like, we have another starting point here, the subquery, because that's the person. So we start by label scan, right? And we have, in total, we have, so that's like this. Because we indicate it's a person, so we don't need to scan everything. So we do a label scan, and there's 133 like a person node. And now, because we're doing a matching and unwind, so we try to see, so there are two rows and indicating two values, and for each value we want to see if it's here. And here the database is actually not very smart in implementing this. It's using something called apply. This is called apply, and it works by performing a nested loop. It's a nested loop because we have two, on both sides we have multiple things, right? Here we have two rows, and here we have many nodes. So when we have, it's like we have two lists. When we need to traverse the two lists, we need, and we to match them one by one, we need a nested loop, right? So that's why they have an apply. And this is the outer one, and this is the inner one. And so every row being produced on the left hand side will then, so like this is the outside, and then every value, the row is basically every value, will be applied here on the right hand side. So that's why we actually obtain this record twice, because for each value, basically we do a node label scan. And we have two values, so we get it twice. And then we do the filtering. And again, we have to filtering twice, because each time we have to check, okay, if this value is in the phones of that node. And if there are 5 times, if there are 5 phone numbers, and this will do like 5 times, or everything will do 5 times. So this is a bit not very efficient, but that's the typical way, basically, you do a nested loop. Okay, so that's a relatively complex query plan, which have something called apply. It's like doing a join, right? And it's not very efficient. It will be quite costly. And sometimes we can write the same query in different way, right? And really depends on the version. And then sometimes the two different, they produce the same result, but they write in different ways. And sometimes the different ways will have quite different execution plan, and one will be better than the others. So this was an example I used early on, but in current version, actually version 3.2 and after, these two queries basically will have very similar performance, but in early ones it's not. So that's some query you've seen in last week. So we want to find all movies released like either in 1999 or 2003, and we can write it in 2 ways, either this way or this way. So by doing this way, in the early version, because we use an in operator, and even though we have index on the released property of movie node, and in the early version when we are using it like this, so it doesn't really do using the index. It do a node by labels scan, so it find all the movie node, and then do a filtering, like check if the release property is either this value or this value, and then do a projection, and then do the others. But in later version, which is a bit more smart, so it will read this condition, and it's able to use an index to find the movies, to locate actually the movies that satisfying these conditions. So it will start with node index seek, which is more efficient than this one, and then the rest is then after that just do a projection. Now, if we write it in this way, so basically they produce the same result. Well, the performance actually is slightly different, not exactly the same, slightly different because of the apply. When we do unwind this as year and then match movies and where release year equals year and return title and release. So this actually is not as efficient as this one. So you can even, the query looks more complicated and the execution plan is actually more complicated. It has apply, and when we has apply basically, and this is all right, it has two rows, and then there's a nested loop, right? And then we have to do this twice because there's two rows, and then we do the like node seeking twice, and we have to do this all the other things, subsequent things like twice, depending on how many values, number of values you have on this side. And when you do apply, basically, that's a nested loop. It's not actually as efficient as this one. But could be more efficient than this one, because this one is scan all the node, and this one, again, we use index. And then if here we don't have many values, and this plan could be more efficient than this plan, but it's definitely less efficient than this plan. Okay, now let's see another example of comparison. The question is, now we want to find a list of person who has acted in at least 3 movies and also directed at least 1 movie. So yeah, we want to find someone who can direct and also act. And we do have we need someone who have acted in quite a few movies and direct at least 1 movie. So we try to show you those comparison is try to give you an idea that, okay, Cypher is very powerful and flexible. So the implication is it's possible to write very different queries that will produce the same result. And depending on how you interpret like the steps. Because you write a query, it's like your query is mimicking your mindset, how you think the system, well, the server should answer, like find things. And then, depending on how you express this, it's more like a step-by-step, like procedural way. And if you're not very careful, you might write a query that is not very efficient. And then the different ways might have a very different performance. So you can't really rely on database engine to rewrite the query for you. So this is the same for MongoDB, because both MongoDB and the Cypher, they write query not following any mathematic ways, not like SQL, because SQL is governed by relational algebra. And relational algebra has a lot of features allow you to move things around. And then there's theories saying that, okay, you can do this and it's equivalent to that. So there's mathematics theories governing this, allow you to basically rewrite SQL queries. But MongoDB query and Cypher query doesn't really have any math behind it. So the server will not try to rewrite your query, because once you rewrite, it may be totally wrong. It can't really guarantee still produce the same result. So then it's the burden of the developers basically to write the query in a proper way, and then it will have desirable performance. Okay, now let's see. I'll show here. I'm going to show you 2 ways of writing queries to implement the result. The first one is more like a very step-by-step one. So first, because we want to find a person that satisfies 2 kind of things, that acted in a movie or and also acted in also directed a movie. So we first, like we do it step by step. We first find out all the persons that have been acted in at least 3 movies. So like, and persons acted in movies, and then we do aggregation, and then we do the filtering, right? And once we find that person, so that's like we reduce, we find the subset of possible persons, and then we try to see if the person has directed some movies. So I deliberately write it in this way, but I know you usually you might start from direction, right? Because that's, you get less result. But anyway, I write it in this way to make the performance pretty bad. Okay. So first, it will start by node label scan, because there's no property involved at all, right? So we start from, like, our query is indicating there are two types of node involved, the movie node and the person node. So we need to start from some node. And because we start from the movie label, because there are less movie node than the person node. So here we have 2 options, but we're using the statistics, and now we know there's a much less movie node than the person node, so we start from that. So we'll start with the movie, and then we do the expand like this. So we try to find all the acted in relationship from the movie node, and then we expand that. So after we expand that, there's no guarantee on the other side. Sorry. Yeah. It's this one. And so there's no guarantee on the other side the node is of person type. There could be, well, system doesn't know, but we know it has to be of person type, but system doesn't know. So it needs to check the other nodes are of person type. So there's a filtering. Yeah. But it won't really change anything. So it's 172 and 172. And then we do aggregation. And once we do aggregation, we do the filtering. And this is not very sure. I think it's, again, like early version has a projection and filtering, but the later version you only find a filtering. And then once we done that, we have a subset of like the persons. Now it's from 172 rows. This is down to 102 rows because that's the unique number of person. And then after we've done the filtering, it's down to 15 rows. And then we try to expand for all the 15 person that acted in 3 movies, at least 3 movies. We try to see if it's directed some movie. And now we only find 1. And then that's the result. And then return the result. So that's one way of writing it. And the other way is we can actually we can match a much longer pattern. Instead of doing one by one, we put everything in together. So we want to find a person that's acted in some movie and also directed some movies. So we want a much longer pattern. We want a much longer pattern. And now we can't, now we do the aggregation and make sure the person has done acted in at least 2 movies. So this, again, will start with because it involves person and movie, so it starts by node scan and to find all the movie node. And because we have actually two movie node here in the pattern. And the system will use some statistics to decide, am I going to start from this end or from this end? So the statistic they use is, it will look at the relationship. It figure out, okay, we have a much less directed relationship than the active relationship. So we start from here. That will give us much smaller subset to work with. So it starts from here. So this basically means that one. And then we're not trying to expand the whole thing in one step. So it's actually do it one by one because we do need to check it's the correct type. So we start from this side, ensure we get as minimal a subset as possible. So the expand is like doing this, only expand the direct relationship to find all the passes that, basically to find all the persons like directed some movie. So we have 38 movies, nodes, and plus 44 direct relationship because some movie has more than one directors, right? And then we need to filter here, because after we expand, we can expand to any node. We want to make sure it is the person node. So we do a filtering. Yeah, we do it's for 44% node. So the filtering doesn't really filter out anything. And now, and then we try to expand on this side to see all the active ones. And we get 18 moves. So you will see here, we're not, so most of the results are not very big, right, comparing with the other ones. So now we do another one. And we expand, and so among that, only 18 are of the directed. Then we obtain this, because again we have to do a filtering, make sure this is on the other side is a moving node, because now we start from person node, and we want to make sure once we expand following the acted one, acted in relationship, on the other side is a moving node, so we do a filtering. And now we do aggregation. So it's memory processing. So we're aggregating much less data now, because in the previous one we're actually aggregating a lot of data, right? We're aggregating like for every person that has acted in the movie, we do aggregating. Here is we're doing a very small aggregating. So it's much more efficient. And then we do the projection and other things. So this is compared with the previous one, where we have a lot of node, and then after we expand, we got so many rows, and we do a much more. We aggregate a lot more data here compared with here. So that's a much better option. Yeah, something worth mentioning is Neo4j does support transactions. Its database is not like distributed. It's on a single system, so it's much easier to implement transaction. It's actually support full ACID transaction, very similar to those in RDBMS, and then it also using similar technologies like locking and other write-ahead log and other things that you will find typically in any storage systems, which we're not going to cover. Next thing that worth mentioning is some very general principles when you're doing data modeling. Most of these are kind of intuitive. Because this data modeling is very closely related with domain modeling, like when you are doing requirement analysis and you try to see what data your system needs to handle, so you do domain modeling. And if you use Neo4j as your backend database, actually domain model can, most of the time, majority of your domain model, like the one you draw, like your object model, can be converted directly as the property graph model, because they're very closely related. And basically you need to decide for something, is this like a node or a relationship? And most of the time it's pretty obvious. And also for something, whether you should model it as a node or property, or if it's too small, we should model it as a property. And there's another thing is like, do we model something as the label or type, or should we model it as like a property? So there are a few decisions to make. Some are pretty obvious, and then you can make decisions easily. Others are less obvious. So decisions are based on like the features of the entities in application domain, like whether it's very complex or whether it represents something, or your typical queries or the features and constraints of the underlying storage system. So that's a very a very general principle. Most of the storage systems, when you do the design, is like that. Okay, let's see how do we decide on node and relationship? That's usually pretty easy, and most of the time very obvious. When you see something, you know that looks like a node and this looks like a relationship. So basically, nodes is like for things, or relationship is like for structures. So if it's like a system where we're modeling like user read the books or likes the books. Like as a reader who likes a book, I want to know which books other readers who likes the same book have liked, so that I can find other books to read. It's like recommendation, how we can recommend books. So this is the node and the relationship here is really typical and obvious, right? So there's a reader and there's a book. They are like things. So usually you model them as node. And there's likes relationship, like a reader likes books. And they are like, they like structure. And very likely you model them as relationship. And your graph would be something like this. A reader likes a book and then a reader likes this book. And this recommendation type of thing can be converted into a query like this. Like a reader named Alice likes some book, likes a book called The Dune. And now we want to find someone else who also likes these books, and then the other books that liked by this person. So we try to match like a long pattern like this. And then we return this other book. So this is, okay, I'm liking this, and then we find someone else also read like this, but then we find other books liked by this person, and that book probably I will like. And then just return the book title. So that's relatively simple. And most of the time, yeah, you can easily make these decisions. And sometimes it's not things, but more like a fact. But still, they're kind of obvious. Like if we have film, we have someone written review, and then in the magazine. So again, you will easily model like a film as a node, and the person who write the review as node, and the review itself, even though it doesn't really like a thing, but still it's something. Right? You model it as a node, and the magazine is like thing you model it node. Or this is more like a fact, not a thing, but more like a fact. So if we have like a performance is based on some stories, and the performance is, and then we also want to see who performed in which performance and as which role. So again, all of these things, you model them as node, and then this is like relationship. Okay, this is based on this story, and it has this one is performed here as this role doctor. Okay. Sometimes certain things are a bit like a property, but as a property, they're quite complicated. It's like because they have sub-properties. So you can promote that as node, right? So this is similar when you do class design, and then some property is really like a complex class, and it becomes a class itself. So like here, so complex value type usually is represented as node because you want to identify the sub-properties. Like the address has lots of sub-component, like address. So we have a user. Address is like a property of a user, but because it's pretty complex, so we model it as a node. And then the relationship is, okay, this is user's delivery address, and this is user's billing address. And at the same time, we add address. We add a generic address there, relationship. So we add a lot of relationship here. And in the next slide, you will see why. Okay. So another thing here, we actually model something. We model certain type as relationship type, right? Because this is a user's delivery address, and this delivery address is like a type of relationship. And this is the user's billing address, and we put this billing address as the type of the relationship. But there are other ways of modeling it. So we might just remove this two relationship, and we keep this, and we add a property here. The property will say type, like billing address, and this will have a property like type delivery address. So that will model the same thing, right? It still tells, okay, this is the delivery address, that is the billing address. So how do we decide? Okay, so we can use fine-grained relationships, like, so instead of just have a generic relationship called address, we might differentiate between home address, billing address. Like if we know we only have a very finite, a closed set of relationship types, and we know beforehand these are the types we're going to use, maybe only 2 types, home address, billing address, or maybe business address, maybe 3 types. And we can use this. But if we don't know, and if the type of address will keep like increasing or keep changing, it's pretty dynamic, and then using it as a properties value is much more easier to handle. Or, so using this is actually not as easier as the other one. Like if Traversal would like to follow, if you want to follow a particular type, that's okay, like all the home address or billing address, that's fine. But if you, then using type is probably good. But if you want to follow generic type like address, we only find all address of a user. We don't care whether it's a home address, work address, delivery address, or whatever address. Then we have, if we use this, it's not very, well, when you write a query, it will look a bit complicated because you have to have a lot of a pipeline here indicating either this or this or this. And if there are 5 of them, and then the query doesn't look really nice. And then sometimes that's the reason we actually add a redundant generic one here. So we can only use the redundant one. Or if we know the only type is address between a user and this particular node is like some kind of address. And then we don't need to worry. We can write query like this. Okay, so that's, again, it's just some pointer to you. Like, okay, Neo4j does have implement actually a lot of graph algorithms, and the set of algorithms implemented, it's increasing in each version. So it can do a lot of common graph algorithm, but it's not part of the database itself. You really need to download it. And they are implemented as procedures, the Cypher procedure. It's like SQL's procedures, and they're written in Java and can be executed on the server side. It's pretty efficient because it's on the server side, so it's very efficient. Okay, yeah, that's all for this week. So the lab, it's still, the Neo4j running queries, inspecting the performance.